Now, if you think back to when I showed you the observations, I showed you that the land is now warming faster than the ocean already, and we're seeing a lot of evidence for change in the Arctic. Let me run it again very quickly here, and let's stop it somewhere around here, and I'll go a little bit further in here. Whoops. Maybe you can see that there's some spots up here that actually didn't warm, and there's some around Antarctica that haven't warmed. This relates to changes in ocean currents. And so the Gulf Stream comes up here. If you shift the Gulf Stream south, for instance, then you can actually get a cooling in some parts of the ocean and around Antarctica also. There was a movie that took this idea, that change in the Gulf Stream, change in the thermohaline circulation, as it's called in the North Atlantic, developed it into a movie called The Day After Tomorrow, and they actually turned it into an ice age. They said, oh, this cooling is going to overrun, and you'll end up with big sheets of ice all over the place. And of course, that was science fiction, but it was based upon a little bit on this idea that the changes in ocean currents could be important. So 100 years from now, if anything like this were to happen, we could have rather a different planet. This is the prediction from the climate models for 2090 to 2100. Remember what I showed you was already happening with regard to changes in precipitation, namely that the northern regions were getting wetter. In fact, the snow season's getting shorter. There's more rainfall. The atmosphere can hold more water vapor. This is what the model suggests is going to happen. This is December, January, February, so this is northern winter. This is June, July, August. And it suggests here that the northern regions will continue to get wetter. But, and right in the monsoon belt, where the monsoon rains occur, it also will get wetter. But here you'll see a lot of the action is out over the ocean, not over land. And what you see is all these brown regions in the subtropics in particular, and extending up into Southern California and the Southwest in December, January, February. And, hints of this also up in here. There's less agreement in this particular region here in June, July, August. But these are areas where it gets drier, and so the risk of drought really increases substantially, and there's a very large-scale pattern associated with these. This is the change in sea ice. This is the actual average from 1990 to 1999, which is very well replicated by our model at NCAR. And this is the projection in the model from 2010 to 2019 in terms of sea ice compared with more or less today. And then this was the projection in our model from 2040 to 2049, basically an ice-free Arctic in September. And of course, this is the Northwest Passage. And the Russians, this year, after the big drop in ice, went out and planted a flag at the bottom of the ocean in the North Pole. This is where, of course, the polar bear runs into great jeopardy. But rather than being upset by the polar bear, everyone's excited about the Northwest Passage. Well, this is what the NCAR model showed, and this was published in an article actually in 2006. And this is the observations in red here, and this is what the NCAR model showed in terms of Arctic sea ice. Small decreases, but then it showed this rather abrupt drop in the 2030s. And as soon as you start to reduce the amount of sea ice, then you get an albedo effect. The less ice means you've got more water, which is darker, and so there's more absorption of solar radiation, and so there's a runaway amplification effect. Instead, what has happened is this is the 2007 value, and it looks like our model is the best in the world at doing this. The other models tend to be more conservative, and the IPCC projections for sea ice is that this kind of thing would not happen until, say, the end of this century. Instead, Mother Nature tells us that something is going on already. I mean, this is zero down here, and we've lost 20% of this amount of ice. And so something like this already seems to be happening. This is a historical perspective now, going back now 450,000 years, and we can do this now back over 600,000 years. This is the temperature record from Antarctica from an ice core. This is the methane record, and this is the carbon dioxide record. And they tend to go up and down more or less together. 20,000 years ago was when the peak of the last ice age occurred. The temperatures were some maybe 6 or 8 degrees Celsius lower than they are today. Today is over here on the right-hand side. 120, 130,000 years ago was a period, an interglacial called the Eemian back in here, and there are other interglacials. These tend to occur every so often, every 100,000 years or so, and they're mainly associated with changes in the orbit around the sun. The changes in the precession of the equinox, which has a period of about 20,000 years, the change in the tilt of the Earth's axis, which has a period of about 40,000 years, and it changes in the shape of the Earth's orbit, which has a period of about 100,000 and 400,000 years. And that's the main pacemaker that drives these glacials and interglacials that have occurred in the past. Going along with these, following them, are changes in methane and carbon dioxide. We think probably a couple of hundred years behind this, but for the most part, they tend to line up given the time scales that we've got here. And what happens when things warm up to the carbon cycle? Those of you who have a compost heap or anything like that will know in the summertime the bacterial action is much greater, and if you get a frost or in cold weather, it shuts down. So when things warm up over land, you get melting of permafrost, you get a lot more bacterial action. If it's wet, you get marsh gas, which is methane, anaerobic processes, a different kind of bacterial action that converts the litter, the carbon that's in the soils, into, in this case, methane. If there's oxygen involved, aerobic conditions, so that it's dry, in other words, you get carbon dioxide. A different kind of bacteria tend to take over, and you generate carbon dioxide. And so these things follow from processes like that. Now, a lot of it also involves changes in the oceans and the ability of the oceans to absorb and release carbon dioxide. As you warm up the oceans, they cannot hold as much carbon dioxide. You know, carbon dioxide are the little bubbles of air that are in a soda that you drink. Or if you have a kettle of water and you put it on the stove and you heat it up, bubbles come off because as it gets warmer, it can't hold the air that is dissolved in the water as much. And so it's a similar thing here. But what happens now? This is the last 100 years or so blown up. So the temperature's gone up a little bit. Here's methane. This is the historical values of methane. Here's carbon dioxide here. Now we can go back 600,000 years from Antarctica reliably. Before that, the estimates are not as good. But the estimates are that these values of carbon dioxide have not been seen for over 6 million years. If nothing gives you pause more than anything else, doing this to our atmosphere with these greenhouse gases that change the radiative balance of the planet should give you pause. This is the historical context of what's going on. This is the projection for the next 100 years overall. Here's the last 160,000 years, just to give you the context. Temperature is likely to go up here, and carbon dioxide currently we're up actually around here, and in the current rate we're going to be hitting over 700 parts per million by volume. Remember, the pre-industrial levels are somewhere around here, around 280 parts per million by volume, and during the Ice Age they were down around 200.